Welcome, ladies and gentlemen, to our second talk of the day here, From Vision to Action, Designing and Deploying Effective Computer Vision Pipelines. I'm joined here today by Jeroen, by Wesley Boerijk. Sorry, yes. Jeroen couldn't join us today. Wesley Boerijk is the lead machine learning engineer at Accelerated, working on very cool projects. He'll guide us building robust computer vision pipelines using open source tools, sharing real insights from real world applications like predictive maintenance in the Port of Rotterdam, a very cool project if you ask me. So whether you're an expert or newcomer, this session promises practical knowledge to design, deploy, and maintain impactful computer vision systems. So have a warm welcome for Wesley.
All right. Thank you. Good morning. Welcome to my talk, From Vision to Action. And let's start the day with a few questions. First question, who has used or trained a computer vision model once? Okay, quite a bit of hands. Let's go to a second question. Who has ever deployed a computer vision model? Yeah, a few more hands. And then the last question, who has ever maintained a computer vision model in production? Okay, few, nice to see that. My goal for today is to bring you from question 1 more to question 3 and get you some insights on how to do that. So what's going to be the topic for today? It's going to be computer vision and it's going to be MLOps, but not the two topics in isolation because there's already a lot of information out there. But today I want to talk about the intersection of this, how the MLOps practices changes when we're talking about a computer vision project. What the interesting things are that we can learn from, what the insights are. So, who am I? Who are we? My name is Wesley. I was supposed to be here with my colleague Jeroen. However, his wife gave birth yesterday to their newborn kid, so that's a perfect reason not to be here. We already anticipated on this, right? There was a due date, so I'm fully prepared to deliver this on my own. But I did this project together with Jeroen. So I'm Wesley. I'm the lead ML engineer at Accelerated. Jeroen is also an ML engineer at Capgemini, different companies. So how is it that we happen to do a presentation here together? And that's because we work together on a project for Port of Rotterdam. Which project? What was it? It's a computer vision project. It was for the asset management department of Port of Rotterdam. And they are responsible for the road and waterway infrastructure to keep it all on a high quality, to make sure there's no safety incidents, to make sure that the port is in the best shape as it can be. To do so, they have to maintain an area of over 100 square kilometers and make sure all infrastructure is good there. And they do a lot of inspections there. But there's a few drawbacks on doing these inspections by human. It is time intensive. It makes it expensive because it requires experts driving up and down the harbor all the time. And it's sometimes unsafe. They use these vehicles to do their inspections. They cannot do it while driving, so they have to stop on places where you're not supposed to park. You have to get out of the car. You have to do some kind of measurements, all for, like, there's a lot of trucks driving through the harbor. So that's something that's not ideal. To give an idea of the shape of the area that they are inspecting, this is the road from the World Port Center, the headquarters of Port of Rotterdam, all the way to the second Maasvlakte, like the newest built part of the harbor. And it takes about 50 minutes drive over the highway to get there. So when they're tasked to do an inspection all the way over there, it already takes them 1 hour to get there and 1 hour to get back. And we thought, okay, we can do this smarter. We can actually use video and use computer vision to automate some of these inspections. That's how the idea of the machine learning inspector was born. Here you see the same car, the same yellow hood, with a camera set up on top. And you see that we take videos and we detect and classify assets that you see on the screen to assess whether they are damaged or not, to assess whether there's something that needs to happen to make a corrective action on one of the assets in the harbor. And today I'm going to tell you how we built this project, what we learned from it, and also share some lessons that you can also enjoy, the mistakes and the lessons learned from that. So let's talk about some of the use cases. Things that we see in the harbor are damaged traffic signs. These things don't last forever. Here's an example of how they look when they're damaged. Another one is skewed lampposts. This is a safety issue. Here we see one that is like tilted backwards, but they can also be tilted forwards. And if you have a large truck and you drive past it, you can hit it with all consequences from that. So I take these two examples as use cases that we've worked on throughout the last 1.5 years and take you on a journey how we built this project. Let's actually start at the end. How should this project look like for the end user? In the end, it's the asset managers responsible for maintaining these assets, and their ideal wish is to get like a map and get an overview of what the quality is of all their assets that they're managing. Here's an example of the map of Rotterdam, the harbor, with dots all over where we did inspections. I can zoom on a bit more on a specific harbor. Here we see all dots where we did inspections, and the idea is that if you click on one of them, that you can see like what the specific inspection was. You can see like a picture, and you can see if there was damage, and you can change the status if there was like a mistake in the damage classification. If there needs to be action, it can be taken right from this system. So this is what we want to build, and now I'm slowly gonna build up how we got to this result. So from the use cases that I just explained to how we designed this system. And we're going to build a pipeline. This talk is called Computer Vision Pipelines, so we're gonna build a pipeline together, and we start at the start. We have a car with a camera setup, and later also a ship with a camera setup. And from that, we get a stream of video and a stream of GPS points to know the location of that specific vehicle. Those go into a building block that we call video ingestion and anonymization. And out of it comes individual frames with their GPS tags for each frame. We build all the steps of the pipeline as microservices, so they're like individually contained and they have an interface, what goes in, what goes out. Also important to say is we put the anonymizer right here at the beginning because we're taking videos in a public space and we're not allowed to systematically register information about people. So no license plates, no people, no faces, all these things gets blurred out from the moment that we start processing them. Then the second step is actually detecting the assets that we see on the frame. And we use a segmentation model for it. You actually have a choice between like object detection or segmentation. We chose to go the route for segmentation because it gives us the masks, the polygons, to actually fully know which pixel belongs to which asset. And you see that we have like the model encapsulated in this system because we want to swap them out and we want to retrain this model and replace it for a better model once we get a chance. We use open source modeling, open source tooling, and right now we're using the YOLO V8 model, which is the first YOLO model that actually does segmentation and not just object detection. So after this building block, we get detections, which are bounding boxes plus these segmentation masks, and they go to the next step. The next step is object tracking and localization. In a bit, I will explain more in detail how it works, but for now, we need to understand that when we take a video, we have a lot of sequential frames where we see the same asset, like the same physical traffic sign is what we see in the harbor. But if we analyze each individual frame in isolation, then we get a lot of duplicate results. So we want to trace back the objects that we see over multiple frames. We want to combine that to give it one ID for an asset. That's what we call a tracked object. And then what we also do from the bounding box and the segmentation mask, we're able to make like a crop from this asset to not have like the full picture, but just the asset that we're interested in. And that's going to be the output of this third step of the pipeline. Then we arrive at a point where we have like asset-specific models. And here we can make a model for skewness, for example. So what goes in is the picture and the mask of a lamppost. And what goes out is the decision whether this asset is damaged or not, whether it's skewness or whether it's a traffic sign that gets damaged or whether it's any other use case. We kind of built this modular pipeline where we're able to add new use cases into this whole system quite easily. And then lastly, when we have this, we can publish it to the dashboard, make it available to the end user, to the stakeholder, and from there they can continue to do their job without requiring them to sit in the vehicle, drive through the harbor, and jump out of the car to do inspections. All right. Now I want to dive a little bit deeper into some of the components to show like what they do, how they work, and after that we proceed to like what the most interesting lessons are that we learned from this project. So object tracking, like I said before, one physical asset actually has a lot of captures on the video. Here we see two examples, one traffic sign with 28 observations and one with 46. And after we applied our tracking model, we see that we get a nice centered crop on each frame for this asset, and this is input for the asset-specific model, like the damage classifier that we see. How this works is visualized here. We actually use a method of centroid tracking combined with some embeddings to get like similarity between embeddings on these crops to make sure that we can do this. That was pretty tricky because most object tracking systems are designed for a stationary camera where something is moving on the other side, but here it's the opposite way. Here we are moving from the car and the objects are stationary, and therefore most methods that are already out there didn't work right from the get-go. Then another step that I want to highlight is the skewness. I want to show you how we calculated like how skewed such a lamppost is. And we basically take this as input. We have a video here where you see a number of lampposts, and then like somewhere near the end we see a lamppost which is like skewed back a little bit. And with just these segmentation masks, we're able to calculate the angle at which this one is skewed, because that's the exact information that the inspectors and the asset managers want to have. How do we do this? First, we take the original frame. Then we take the segmentation mask, and it's important that we cut off the head of the lamp to just have like a sort of straight view of this segmentation mask. Third step that we do is rotate this 90 degrees, and then we actually take a linear regression through this mask. Every white pixel is like a hot pixel, as we call it. Every black one is a 0. And we basically just draw linear regression through this mask to get the slope of the angle that we see here. And from that, we can actually calculate the angle compared to the horizon that we have. In this case, it's an angle of 6 degrees, and this is also the threshold for Port of Rotterdam to replace a lamppost. So when it's over 6 degrees, then it's a hazard, potential hazard, and it has to be replaced or at least maintained. One last step is this is skewness compared to the horizon, but maybe this horizon is not straight. Maybe the car is tilted a little bit, maybe you drive through corners, maybe the camera is not mounted perfectly horizontal. So what we do is we actually calculate the median skewness of all lampposts that we see in the same video, and then we calculate the relative skewness compared to the median, basically, to offset if there's like something weird with the setup, basically to get more consistent results. Then the third and last component that I want to highlight today is the model for traffic signs. Here we chose to make a classification model based on a ResNet 50 that we take from torchvision, and then we apply transfer learning to a lot of like cropped images of damaged and also like good quality traffic signs that we have to basically do this binary classification. Say, okay, these ones are in good condition, these ones are in bad condition, like these are damaged, to separate them from each other. This is a bit of a simplified view because here I only take one image, and in reality we take the whole tracked object. So we take all the crops and we take like the mode, like the most frequent estimation of what the model says. And here also we only take like damaged true or false, but in reality we have multiple categories on which it can be damaged. It can be like the coating, it can be like decoloration, it can have dents and holes in them, it can have graffiti on them. So there's a bit more to it, but in essence, this is what we're doing. And to show you like what makes a bad quality, I have some examples. So here we see some traffic signs that have quite an ugly coating, I would say, but they're still functionally okay. Here we see ones that are like almost unreadable, so these need to be replaced as soon as possible. And then the hardest problem is the one of offensive graffiti, because we can detect graffiti on signs, but it's pretty hard to detect whether it's like offensive, like what's on the graffiti. We still need a human in the loop to actually decide whether, like what type of graffiti there's on this sign. But still, we're able to detect the graffiti, so that's a good thing. Okay. Now I want to continue to the part where we have the MLOps part of the project and the computer vision pipelines, and what like the special cases are that you maybe not see in a MLOps setting without computer vision. First thing I want to highlight is how we actually orchestrated this pipeline, and we did this based on Argo workflows. So in the bottom we see the pipeline that we built along the way. Just to highlight it again, we built every step of this pipeline as a microservice with a fixed interface, so we can like swap them out, but also as an installable Python package that we can unit test and build confidence in them. And the nice thing is that since they're all Docker containers, we can run this on Kubernetes, and we can use Argo to for the workflow execution and basically define how these steps in the pipeline run sequentially. Some can run in parallel. Some need a GPU because it's either a training part or like an inference on the video. Some are pretty lightweight, so they don't require a GPU. And after all, these DAGs, directed acyclic graphs, are all defined in YAML, so you can define them in your Git repository. All right. Second, like hard thing that we had to overcome was how we manage our annotations. We have training data. In a typical fashion, you have like tabular data, and you basically have, you can make like snapshots of this, but here we're talking about images and labels and annotations, and how do we build on top of this? In the old version, this is how we started out. We had segmentation, we had like a folder of images, and then we had JSON files with like all these labels, but then when you add an asset, you have to go back to your original images, and then you also have to annotate this part, these assets, and it became like a big jungle of like files laying around and folders with images. Same for classification. We set per asset, per damage category. We make like folders with good quality, bad quality. But this requires to save your images multiple times, and is not the best solution. So we transitioned into something more scalable, and that is to put these labels in a database. So what we did was create a database with a label per asset type and per damage category. This requires us to save the image once and just refer to it according to like a certain file name. And we created an append-only functionality. That means that we can create more labels for the same image if the label actually changes. If we made a mistake in the training set and we see that after we do our validation, and we can retroactively add another label and use the latest one. And that's how we enable data versioning, by querying this database and say, hey, I want the data set as is, it looked on this specific date. That means it looks a bit like this. Let's say we start out with this small data set. We have images A, B, C, and D. 2 of them are bad, and we added them on the 1st of September. Then a week later, we add 2 more images on the 8th of December. Then we add another label, because we found out that image B was actually good quality and not bad quality. We see that we added this on the 12th of September. And if we now query the database to make to start a new training pipeline, we can actually like omit this line from the database and keep the other ones. And if we would want to go back to see, hey, how did our model actually train before this, we can query this table from a previous date, and we still have the exact same labels without saving any information twice. All right. Third part that we want to highlight during the MLOps versus computer vision is how do you do validation and integration testing when we're talking about models that work with images. And basically what we did was we annotated a full video with all the segmentation mask, classification properties, the tracked objects, to be able to make performance metrics over a pipeline run. So it's kind of like the last step in our CI/CD pipeline. It runs in Argo, though. The idea is to fully annotate something, and whenever we make a change in our model or somewhere in the pipeline, we can run this again and get like these performance metrics. Like for segmentation, we can take the IOU. For localization, like the mean absolute error, precision recall for each individual object, to guarantee that you have like a model that works well in production. All right. Then let's proceed to the last part of the presentation, the lessons learned that we had from this project. Typically, we learn as humans from mistakes, and we also take this concept of having our machine learning model learn from the mistakes. Because ML models create a lot of false positives and negatives, and it's hard to adjust the actual model to account for these specific things. They're rather complex models. We use transfer learning to train them. And then we're rethinking this as a data problem, because we simply did not give the model enough data, enough opportunity to learn this specific example. So what we did is adding all false positives and negatives to the training set, such that in the next iteration, when we train the model, it's at least able to learn these mistakes that it did the previous time. And here we can also use a feature from the dashboard, because the end users are actually able to correct mistakes that the model did, and these mistakes can then be fed back to the training pipeline to make sure we have a continuous learning setup. What we also found was that there is quite some disagreement between how we annotate the labels. The perspective of a stakeholder was, okay, now that we're doing inspections with the computer means we should be more objective and more consistent with how we classify our assets, right? Well, the inspectors disagreed on up to 50% of the annotations in a setting of like a multivariate classification model, which means like the data set is not even like unified in its decision. So if we train a model on this, of course it's not going to be objective and consistent. So this gave like a false sense of confidence in the model performance, and we actually had to make the problem simpler to make sure that at least the inspectors, the humans, agree on what they're doing before we start teaching a model how to do this, how to automate this. So my takeaway here was to always build the simplest version first and then iterate over it instead of trying to make the complex version. Lastly, there is this thing of detecting things that are not there. This is one of the questions that we got along the way. Hey, can you detect things that are not there? Let's say there's supposed to be a lamppost here, but it's missing. This is kind of a non-computer vision problem, because you cannot detect what is not there. But still, there's a way how to deal with this. Because if we drive past this street, past this invisible lamppost every time, and consistently we fail to recognize it, if we have enough passes in this same street, then we can actually make the case like, hey, we don't recognize anything, but the data says there should be something. So maybe we can actually find things that are missing. Okay, then to summarize, I think these are the most important things that I learned on the intersection of MLOps and computer vision, which is build standalone components that you can swap out and improve over. Organize the training data in such a way that you actually build on top of it, instead of creating this huge jungle of annotation files and folders with images in certain categories. Always build the simplest version first. This is kind of the Scrum philosophy. I think we all know it in theory, but when it's in practice, it's still hard to do, because you always have these ideas that you want to do. start simple, just build that first and then iterate. Learn from the mistakes, do that as human, but also do that as machine learning model, so build this feedback loop if you have the opportunity to do so. Feedback the mistakes into your training pipeline such that you don't make those mistakes again. And then lastly, think about how you want to validate and integrate, do integration testing for your models. Because that's the only way how you can build confidence in your model outside of your training pipeline and inside of like the production setting. Then I want to show my gratitude to all the open source components that we use in this project. This project is fully built on open source. These are the ones that we used, and we would not have been able to achieve this without these components. So thanks for that. And that concludes my talk.